Cheers. I'm Christian. Hello, everyone. And I'm going to talk today to you about cgroups. And first of all, like how many people are acquainted with cgroups in a non-trivial sense? Okay, so I guess you heard, like, over the last day or so, you heard what containers are made of, essentially, and cgroups are one big important part of it. And I'm going to introduce, like, in a general sense, what cgroups actually are. So first of all, essentially, they're nothing but a pseudo file system implemented in the kernel, which follows the VFS layout. Some people are really annoyed by that, looking at Alexa, but they're essentially nothing else but a collection of processes in a hierarchical manner and allow for resource distribution and resource tracking, essentially. Where resources here usually mean stuff like CPU, block I/O, along others, memory, PIDs, for example. And these resources are usually implemented as controllers. And basically, these controllers, what they have, essentially, each controller has a set of files that allow for read-write operations. This is the general idea. And you can either read from those files to get information about resources that are available to a given set of processes, or you can write to these files to implement limits on a set of resources. I think the most obvious controller is usually the CPU set controller for that. And I think we can give a quick... Right, I think we can give a quick demo of what I mean by this. 1 second. Right. Can you see that somehow? Better? Is it okay? Huh? Oh, sorry. Well, then we just leave it there. Well, essentially, what I wanted to say, about this is you can use the CPU set, controller to essentially limit a set of processes to only execute on a given set of CPUs. Like, for example, you could write into the CPU set controller a number, like a range, for example, 1 or 1 to 2 or whatever. And then essentially these processes only have access to this limited set of cores. The idea is obviously similar for memory, only then you write, for example, like how many bytes these processes are supposed to have available. And the cgroup file system, and this is something which not necessarily a lot of people know, for a longer time come in 2 versions, essentially. Cgroup v1 and Cgroup v2. And these are actually vastly different. And the future will be Cgroup v2, obviously. And I'm just going to introduce the 2 Cgroup versions briefly without going into too much detail. So Cgroup v1, you have seen a bit about this yesterday, usually looks like this, where this is the mount layout for the Cgroup file system. Meaning it's usually the v1 hierarchy, or now called legacy hierarchy, is usually mounted at sysfs cgroup, and all of the controllers I referred to before, like memory, PIDs, CPU set, and all of these are usually mounted into separate hierarchies. So all of these directories you're seeing right now are actually separate mount points on the Cgroup legacy hierarchy. But don't be fooled, it's not necessarily the case that you have to mount each controller into a separate hierarchy. That's just the standard layout over the time, basically. But you could easily co-mount all controllers into a single mount point. So then you would have all of the files that each controller makes available under the sysfs cgroup mount point, and then you could like regulate cgroups in a totally different manner than we usually do right now. But this is the default layout we're seeing. And each of those controllers, CPU set, for example, and freezer right here, is, and this is crucial to know, if they are mounted separately, they are separate hierarchies, which means each of those controllers can have a totally different layout, right? The CPU set controller can, for example, you can have 3 cgroups underneath, C1, C2, C3, and each of those cgroups can have additional cgroups underneath, and the freezer controller could look totally differently. It could have a totally different hierarchy. That's a lot of complexity, obviously, but it also allows you to fine-tune the Cgroup file system to basically your workload, which is actually super nice. But the thing is, this complexity we will see will be one of the reasons for why Cgroup v2 actually exists. So what I think about Cgroup v1 is that usually all container runtimes we know, be it Lexi, be it runc, be it Docker, be it Rocket, they all make use of Cgroup v1. Like, this is the standard way of limiting resources on your system for a given container. And it's not going to change that soon, actually. So, but what about Cgroup v2? Like, why does it exist? And what is it? And I think the easiest way to understand why it exists is basically to point out some of the differences to Cgroup v1, because the differences are actually a lot of them. I'm only going to mention 4. So this is the mount layout for the Cgroup v2 hierarchy you see right there, meaning it's usually mounted as sysfs cgroup, and it provides a set of files. And I'm only going to touch on a bunch of them, like cgroup.controller, cgroup.procs, and cgroups.subtree control. It's not necessarily, usually there are more files depending on the controller. But it's totally different in the sense that, for example, whereas in the Cgroup v1 hierarchy, you could have all controllers mounted into a separate hierarchy, the Cgroup v2 follows the strict saying, so to speak, there can only be one. Meaning it is not possible to mount each controller into a separate hierarchy. Instead, the controllers are now basically distributed top-down from the Cgroup or root Cgroup towards the hierarchy, towards like other Cgroups, by writing into a file called cgroup subtree control. And you either prefix the controller you want to enable or disable with a plus or a minus. Minus for disable, plus for enable, right? So you look at the cgroup.subtree control file, and you know that the cgroup underneath will have a couple of controllers available. This is a totally different model, actually. It takes away all of the complexity, obviously, that Cgroup v1 had, like by having them all mounted in a separate hierarchy, but it also takes away all of the flexibility we'd had with that. And now we come to the constraint a lot of people find very surprising, and I'm interested, like, how many people do know what the internal process constraint for the Cgroup v2 hierarchy actually is? Alexa, that's good to know. So the thing is, in a Cgroup v1 hierarchy, with all of the controllers mounted into separate hierarchies, you can have processes anywhere in the hierarchy. Like, if you remember the Cgroup layout I showed at the beginning, if you have, like, for example, sysfs cgroup CPU set C1, and under C1 you have C2 and C3, then you could have live processes in C1, C2, and C3 everywhere. That's possible. Like, you can have processes in all of the hierarchy. Cgroup v2 takes away this flexibility. You can only have live processes in leaf nodes, right? So what it essentially means, this is why it's called internal process constraint. What it essentially means, exempt from the root Cgroup, which allows you to have processes in it, every other Cgroup that is not a leaf node will not have live processes in it. And this is a pretty big restriction when you think about, when you jump to the next point where you think about moving processes between Cgroups and in general spawning new processes in given Cgroups, this becomes like a massive problem, actually, for container runtimes, I mean. So the third one is resource distribution. Resource distribution is also sort of different. As I said, you now distribute resources by basically writing into a file called cgroup subtree control, as I said, enabling a bunch of controller for the Cgroup hierarchy or for the Cgroups further down the hierarchy. What controllers you have available in a given Cgroup you can gather from a file called cgroup.controllers. So for example, you're placed in a given Cgroup, you look at cgroup.controllers, there's a bunch of controllers enabled like memory, pits, and I/O, usually nowadays if you mount the Cgroup v2 hierarchy. And you want to distribute, well, you want to be able to have Cgroups further down the hierarchy to also distribute these resources even further down the hierarchy. Then you write, for example, the memory controller into cgroup subtree control, which means the child subgroup will have the controller available to further distribute it down the hierarchy. So what it essentially means is the cgroup.subtree control file in your Cgroup is not regulating your own resources, but the resources of the parent Cgroup. Which means you should not have access to this file as an unprivileged user, because it means you could distribute the resources of the parent. This is also becomes a problem for container runtimes, actually. And the fourth one is, I think, one of the This is a really complicated one. So it's called delegation containment, and it has to do with migrating tasks between cgroups. So how do you usually distribute like processes along the hierarchy in a cgroup v1 hierarchy? Well, it's pretty simple, right? If you have the privilege to do it, like for example, you can write to the cgroup.prox file in the v1 hierarchy. You just like take the PID, echo it into the cgroup.prox file, and your process has been migrated wonderfully into another cgroup, right? That's all you need to do. Okay, but what about cgroup v2? Can we do this? No. That's the simple answer. What you actually need to do, it follows two very concise constraints, which you cannot circumvent. First of all, you need to have write access to the destination cgroup cgroup.proc file. That seems fine, right? That seems fair. That's something you also had to do in the cgroup v1 hierarchy. But you also need to have write access to the common ancestors cgroup cgroup.prox file in order to move the process. So for example, look at this little hierarchy I showed you right here. It's a unified hierarchy. Let's assume you're now living in cgroup C2. All of your processes are living in the cgroup C2. You know a couple of things. First of all, C3 and runtime will be empty. Also, container 1 will be empty, because you cannot have live processes in leave nodes. It means C2, when there are processes in there, it's a leave node. The other thing is there will be no controllers available for C3, runtime, and containers, meaning that there will be no controller in the cgroup.controllers.file, and there will be no controllers mentioned in the cgroup subtree control file of the C2 cgroup. So okay, now let's say you want to move a process from C2 into C3. First of all, you need to have write access to cgroups, to C3 cgroup.prox file. But you also need to have write access to cgroups, to C2 cgroup.prox file. And that's quite problematic, actually, when you think about delegating processes further down the hierarchy as an unprivileged user, essentially. Okay, I think what I want to stress with this summary is that the way we assume cgroups work right now will be broken when v2 actually becomes a thing, like massively broken. This is going to be a problem, I think. So what does user space actually make of it right now? I mean, a couple of us, which Alexa and I, we have basically tried a couple of times to play with cgroup v2 hierarchy, and it's interesting. And the thing is, not a lot of programs right now use it. Like systemd has gained, as of, I think, version 2.3.2, cgroup v2 support, and since 2.3.3, actually, unless you flick a specific switch, mounts a hybrid version, meaning all of the v1 controllers you have right now, CPU set, network, block IO, and so on, are mounted into separate cgroup hierarchies of version v1. And under the mount point sysfs cgroup unified, you will have an empty cgroup v2 hierarchy, which is internally used nowadays by systemd to track processes. And that's fine. It preserves some backwards compatibility at least, but I wouldn't rely on systemd for that. And I'm not flaming here. The thing is just they have broken user space before, and we had an argument with them about this. When they released 2.3.2, they actually decided that the systemd controller, which was traditionally a v1 controller, was now made a v2 controller, which means that day they broke every single container runtime out there. So this is a real problem. Like when they decide, when certain init systems decide, not just systemd, when they decide to flick the switch and they say, we're either going to mount a hybrid cgroup hierarchy or we're going to mount a v2 hierarchy, things are going to be problematic. Other init systems I know apart from systemd, to be fair, I don't know, they usually don't delegate cgroups. Like cgroup delegation and cgroup organization by an init system is usually a specialty of systemd, and they're totally within their right to do so. It's just a fact. And user space programs that I make directly use of cgroup v2, I'm not aware of, and I was too lazy to look, actually. And what about container runtimes, essentially? Well, I think a switch to the v2 hierarchy will not happen until there's at least feature parity between the v2 and the v1 hierarchy, because what you need to know, actually, is that a couple of controllers, well, I would say a lot of controllers that we have available in the v1 hierarchy right now is actually not available in the V2 hierarchy. So for example, the controllers that are available right now, as far as I know, I/O, memory, and PIDs, and we discussed it yesterday, I'm not sure if the CPU controller has been merged, which is quite an important controller. And the thing is, there was a big discussion at Linux Kernel Summit and Plumbers going on where we sat down with Tijen to discuss this. And the scheduler guys essentially want thread granularity, meaning you can move threads around between different cgroups, right? This is what you can do with the cgroup v1 hierarchy. And Tijen doesn't want this. So basically, until the CPU controller is merged, you will not have feature parity, and the freezer controller and a bunch of other controllers. So you actually cannot switch. You will regress your users heavily. With LexC and with LexD, we rely, for example, on CPU pinning. You can pin or CPU shares and so on, all kinds of intricate ways to administer what your container can and can't do in terms of CPU resources. And without the CPU set controller, we would heavily regress, and we're not going to do this. And I'm assuming that any other container runtime out there that is taking this seriously will not either. So okay, but what actually about mixing legacy and unified hierarchy? And the question is, will they blend? Like, how good can they actually be combined? And I'm just going to walk through a couple of cases and tell you where I see the problem. And the thing is, I would say we usually care about two things, right? We care about creating and populating cgroups, and we care about resource distribution, essentially. So by creating and populating cgroups, I mean that's usually when your runtime sets up your container, right? Before you clone any namespaces, before you clone user namespaces and so on, you usually set up cgroups for your container, which you do still in the host namespaces, meaning you have sufficient privileges to do so, and then you spawn your init binary and hope all is well. And the thing is, there are two cases to consider, I think, here. First of all of the easy cases. The easy cases where this should be trivial to do, at least with the V1 hierarchy, is where you have privileges. Privileged containers, unprivileged containers started by root, because as I said, you still execute in the host namespaces, meaning when you set up cgroups, you will still have root access. Or unprivileged containers that are managed by a privileged daemon. That should also be quite nice. The hard cases are obviously all of those where you care about unprivileged containers, or in a more restricted sense, even rootless containers, where you lack privilege. So what about actually creating cgroups for your container in a V2 hierarchy? This is something I've been thinking about with a couple of people, and you can do it in different ways, but it's always going to be difficult. This is a V2 hierarchy in my case, and I'm going to assume a couple of things to make it easier and actually make it on time. Is, let's say, again, you're placed in C2, all of your processes, you have created C3 and runtime, meaning it will have your UID and GID, and all of the files in these C groups will belong to you. And let's also say you have all the controllers you actually want to distribute further down to your container actually available in C2, meaning cgroup.controllers file will list all of the controllers, memory, I/O, PIDs, and let's assume CPU is merged. You can then distribute them further down the hierarchy. Okay. So what's going on? Could we just, for example, move our process into runtime and then spawn the init binary and have our container live in a sub-C group called container1, which is usually what is done nowadays? Well, no, it's not that easy. These are the steps you need to take, I think. And I'm just going to mention where you need privilege and where I think you don't need privilege, and this is actually quite problematic. So first of all, you need to chown C2 to your unprivileged user. So this requires privilege, unless you're root, because you want to be able to create subdirectories within that C group, right? It's necessary. Then, when you have done this, you can actually create your sub-C groups, make dir, C3, and runtime. And the thing is, you need to move yourself into basically cousin C groups, right? Or sister or brother C groups, because you can only have processes and leaf nodes. This is where it gets nice. You cannot live in C2 and then all of your container processes live right here, because you can only have processes and leaf nodes, meaning you will need to be apart in one C group. So then you'd shown, obviously, the file cgroup.prox file. This is what's recommended, at least on what the kernel says on the kernel page. You'd shown C2s where you currently live in cgroup.prox file to your user ID, so that you can actually have write access to it and read access, which is required for you to move processes into another C group. And then you would assume the next step doesn't require privilege, right? I could just move my UID, my PID further down the hierarchy into C3, and then I'd be done, right? Nope. You need to move all of the processes down the hierarchy, not just your own, because you cannot have live processes in non-leaf nodes. And that also means if there is a root-owned process in the cgroup.prox file, you will not be able to move it unless you have sufficient privilege to do so. Meaning, for example, if your login session runs as root and is located in the same cgroup as you are, you will not be able to move this process out of the hierarchy unless you have privilege to do so. It becomes a massive problem for unprivileged containers, as you can see. The next step, 5, will also require privilege. This is when you enable controllers for cgroups further down the hierarchy. You need to write to the C2 cgroup subtree control file your current cgroup, the controllers you want to further distribute down the hierarchy. Okay? You have done this. Another step where you require privilege, and the rest should actually the rest should not require privilege. For the runtime cgroup, that is basically the parent cgroup for all of your single container cgroups. You write into the cgroup subtree control file again what kind of controllers you want your sub-cgroups to have available. And then you make a container, one directory for your container you want to set up, and then you migrate your container setup process from, for example, C3 into containers 1. Then you spawn your init binary, and the world should be fine, right? Now you have a running container that is in a given cgroup. Well, the thing is, how we solve this problem of setting up unprivileged users for containers is, well, first of all, the idea was can we somehow do it in the kernel? And then there were discussions with Serge and with Eric Biederman and Alexa on how to get this into the kernel and make unprivileged cgroup delegation actually a thing, but it's not going to happen. We can tell from all of the discussions we've had with Tijan and upstream, and this is again not flaming, it's just a design decision he has taken that this is not going to be a thing. This is going to be done from user space essentially. So you will require a cgroup manager to do the cgroup setup for you, or you are root. You have privilege, essentially. The thing is how we did it. We provide a fuse file system called lexcfs, which basically, we touched on this, I think yesterday someone mentioned this. Proc meminfo and proc CPU and so on are not virtualized, meaning if you look at it from inside of a container, even if you restricted it to only a couple of CPUs, you will see all of the CPUs the host has available. So in 2014, Serge and a couple of other guys, and then including me, came up with this lexcfs file system, which is a fuse file system that essentially provides a mocked version of meminfo and CPU and so on to make containers more feel like a virtual machine. And the thing is, we also ship a PAM module, and the PAM module does all of the basically cgroup setup for you. In the cgroup v1 hierarchy, this is quite simple. In the cgroup v2 hierarchy, I'm actually not convinced. I've tried to implement it over the last 2 days or something. I'm actually not quite convinced that it will work nicely. But we can, for example, do steps like chown the cgroup you're in to your user ID, and we can chown the cgroup.prox file to you, and we can maybe create the cousin cgroups for you. And the rest is going to be handled via a container runtime, essentially. But my point is, this is not necessarily the way to go. You will, however, need a cgroup manager to do the cgroup setup for you, at least if you want to run unprivileged containers that don't want to have a privileged helper. So to walk through this real short, a couple of cases where you, for example, let's say you mix unified and unified, right? Not mixing, but you have unified hierarchy on the host and you have the unified hierarchy in the container, meaning you're running an init binary or whatever process that requires the cgroup v2 hierarchy mounted inside of the container. And the thing is, that should be an easy case if both the init binary inside and outside actually know what they are doing, meaning if they know how to handle the cgroup v2 hierarchy. If they don't, you're going to have a problem. But given that the init binary runs a unified hierarchy inside and outside, you should usually be fine. If the init binary knows how to handle the basically migrating task restrictions, right? The other case is, let's say you have a legacy hierarchy on the host and you have a unified hierarchy in the container. This is also something I thought about. Okay, that means usually that you have all of the controllers, v1 controllers, mounted into separate hierarchy on the host. That means inside of the container, the cgroup v2 hierarchy will be empty, meaning it will have no controllers enabled. That should be a fairly easy case to handle. in the sense of a couple of restrictions don't apply if you don't have controllers enabled. Oh, and something I should probably mention, you cannot have a controller both in the V1 and the V2 hierarchy. It can only be in either one. Like the CPU set controller cannot be mounted into a V1 hierarchy and be available in the V2 hierarchy. Not possible. This is another problem. Meaning resource distribution, even if the init binary inside knows what's going on and knows how to behave in the Cgroup V2 hierarchy, you will not be able to apply any kind of resource limits inside. So even if you say, give this container these amounts of resources because we want the program inside to either manage it or the user who is using this container to manage the resources, not possible if the controllers are mounted into one hierarchy. Resource management will not work. And I think the most tricky case is actually where you have the beautiful unified hierarchy on the container and you have the legacy hierarchy inside. You have the unified hierarchy on the host and you have a legacy hierarchy in the container. What you can gather from this is, one, you know that your init binary is not aware of the legacy hierarchy, right? Unified hierarchy, because it wants to mount the legacy hierarchy. So it likely won't know how to deal with restrictions. It cannot apply resource limits if any of the controllers, for any of the controllers that are enabled in the Cgroup V2 hierarchy. That's the next restriction. And how to migrate tasks, like creating additional cgroups. For example, if you now have a unified hierarchy on the host and you boot a container, you can try and start it up and want to have it available a V1 hierarchy, or the init binary mounts a V1 hierarchy, you freeze immediately because you cannot create any cgroups at all. It doesn't know how to deal with this case. Like, it's not smart enough to do what I just outlined before, essentially. And another restriction is obviously as soon as the full switch to the V2 hierarchy becomes a thing, and even if we figure out all of these problems with Cgroup V1 hierarchy, mounting and so on, and creating cgroups for them, you have an additional problem, namely a Cgroup V2 hierarchy will be mounted on the host, and any hierarchies that are not mounted in the initial user namespace where the Cgroup mount is created will not be available to be mountable in a container. You can try it. For example, boot a system where you don't have the CPU set controller or the memory controller enabled and mounted, spawn a container in a new user namespace, new mount namespace, and so on, and try to mount this controller from inside. Won't work. There's a restriction. This is the piece of kernel code that basically says hierarchies may only be created in the initial Cgroup namespace, so if the current namespace is not identical to the initial Cgroup namespace, return eperm. You won't be able to mount it. So it means even if you want to mix for a container runtime legacy and unified hierarchies, you will need to mount all of the controllers before in the host namespace to have it available inside of the container. Again, for this, we have a solution for this with LexCFS, which basically virtualized the Cgroup file system before Surge implemented Cgroup namespaces into the kernel, which nowadays is a thing. It basically mocked how the container sees the Cgroup hierarchy to only grant it access and the view on the Cgroups it actually is currently living in. And we plan on doing something similar with the unified and the legacy hierarchy. And here is my idea for how this might work. So in order, like, I assume that everyone who implements a container runtime wants its users to be able to distribute resources, right? You want to give a container a set of resources, and you want to be able to, your users, to make use of all of these resources. This is, I think, quite important. But as I said, this will be a problem if any of the controllers are mounted into another hierarchy. You won't be able to apply these resource limits. So what we actually discussed at Plumbers was how are we dealing with this case? And the thing is, obviously, we need a translation mechanism. This is like the first thing that springs to mind. We need a translation mechanism between Cgroup V2 and Cgroup V1, ideally, so that if you apply resource limits V2, but it's mounted in another namespace in a V1 hierarchy or the initial mount namespace, and you have a translation mechanism between the two. The thing is, Teach-in said no. So in-kernel translation mechanism is likely not going to happen. As far as I can see it. I think this is quite a problem, and we need to consider how we are going to move on from this. I think one of the possible solutions is, and something I might be working on over the next time, is to basically use LexCFS, the fuse file system we have right now, to provide a mock legacy or mock unified hierarchy. That provides for all of the controllers the files that you usually expect. Then you, from inside, you basically bind mount these into the container. it should respect these cgroups mounts. Systemd, for example, will usually let you alone if it detects that cgroup file system is already mounted right there. Then if you write into one of these files, or systemd writes into one of these files from inside the container, the fuse file system will translate it into something meaningful for the cgroup v2 hierarchy, and the other way around as well. How well this is going to work out, I'm not quite sure, but I'm pretty certain that we need to come up with a solution because cgroup v2 is, and mixing cgroup v2 and cgroup v1 is going to be a thing, and it's going to be actually quite problematic. I know I ranted a lot, but it's actually something, just because we, also Alexa and I discussed this a lot, and it's actually a kind of a hard problem. And I hope, if you have any suggestions at all, if you want to help out, if you have ideas on how to deal this, shout at me right now or come up to me to talk to me later about this. And at this point, thanks for listening. Thanks.
Thanks, Christian.